Okay, very good. Out again without the.
Yeah.
Right.
So I was saying this work is about some work that we did in 2020, 21. Actually, it was even earlier than that when Matteo was an undergraduate doing his undergraduate thesis with me, and then he went on to do his PhD studies at BU. And Federico Ricci-Tersanghi is a friend and a colleague from Rome, who's an expert in spin glasses, and in particular the implication for spin glasses for computationally difficult problems. The idea of this work was to analyze a little bit more in detail some classical problem, which is called XORSAT, in which when you look at it as being a spin glass problem, the phenomenology of the difficulty for the solution for algorithms to find the ground state, and therefore if there is a solution or not of XORSAT, it's not much due to barriers, like big barriers that one has to overcome. Like, for example, when one talks about the phenomenology of Shannon-Kirkpatrick, but rather they're called entropic barriers. Okay, so the issue is that what I'm gonna try to convince you about is that there are not really big barriers to overcome, but there is just a big, flat, huge space with essentially exponentially many paths that can lead nowhere, and just a few paths that lead to the solution. Okay, and when you run a local algorithm to this, like WorkSat, or another family of algorithms, quasi-greedy algorithms that we introduced and studied in this paper, then what's going to happen is that these algorithms will just settle on a plateau of average energy, and then at a certain point, by just pure chance, they will find the solution. This happens in exponential time, and I will show you how to compute this exponential time with a simple algorithm. Now, in that paper, we also looked at the behavior of the adiabatic algorithm on solution of XORSAT by using a different approach than what usually people do, which people usually look at the gap and use the inverse of the gap as a minimum gap over the trajectory as a proxy for the time. We instead we did integration of the Schrödinger equation in time and looked exactly at the probability to get a solution at the ground state in a given time, and then studied it as a function of time. We thought this overcame the difficulties to say, okay, if it's an entropic barrier, the issue is not much about the gap, is as much about the gap as how many states there are above the gap. Okay, so you can get lost in these many states. You can have a small amplitude to tunnel to each of these states, but there are many, many, many of them. Okay, so you just cut the head to the problem and just look exactly at the probability amplitude, the amplitude to reach the next state. Okay, so much for the introduction. So what's XORSAT? Okay, so XORSAT is a formula in which we do a set of parity checks on n bits, and we do n parity checks. Each parity check is you ask whether bit I, j, k, they sum modulo 2 to a given parity that I want. Okay. So you want to solve this problem. You give a set of the M of these three clauses, they're called. So a clause is, well, a clause is satisfied if this is true or not. So you assign this randomly. Okay, these are 0, 1. And these indices are randomly chosen.
So
Yeah.
can you say again, what's the problem?
The problem is I have a set of M clauses.
What and what?
Clauses.
What is that? What's a clause?
A clause is an equation which can be true or false. Okay, so this is 0, 1, and these are bits. 0 plus 0 plus 0 is 0, 0 plus 0 plus 1 is 1, 0 plus 1 plus 1 is 0, and so on and so forth. Okay, so it's a parity check. And so you ask what you want. The problem is there an assignment so that there exists an assignment X in such that all the clauses, CA is true.
And since most people here are physicists, is it easier to just talk about it as some Ising model?
Yeah, exactly.
Yeah, okay.
So if you want, you can, so just since we have a mathematician, let me humor a little bit. So this problem, it's a set of linear equation in a field.
Okay.
It's a set of linear equations in a field. So it's a set of linear equations, it's easy to solve. Okay, the worst you can do is just use Gaussian elimination, which solves this problem in n cubed time. Okay, you can do a little bit better, I think n to the 2.3, something like that. Yeah. So,
And what are the bees? Are they randomly assigned? The bees?
yeah, they are randomly assigned. Okay, so the problem is easy. Whether there is a solution or not, you just look at the rank of the matrix, and if the rank of the matrix is, and then you have at least one solution. Okay, so it's not a big deal to solve this problem. However, Gaussian elimination, so look at the rank of the matrix, all the operations like this, they are non-local operations in the bit space. So any algorithm which does something which is physics inspired, like for example, flipping a bit or 2 bits and so on and so forth, will take an exponential number in the experiences that will take an exponential number of steps to solve the problem. Okay, so this is mathematically easy in some sense, but for physics inspired algorithm, it's difficult. Not only, you can modify a little bit this source set by adding a small, tiny fraction of clauses, which is not of this parity check form, but is something else. For example, you can have clauses like xi or xj or not xj, okay? And add these kind of clauses, which are of the kind of sat, of 3 sat, which is instead is empty complete. You have a tiny fraction of this thing in the mix. So you ask that not only these clauses like this are true, but also clauses like this are true. And you cannot use Gaussian elimination anymore. The only thing we know are things which are local, like make a spin flip and then see whether you have satisfied more clause now than before. And decide which flip to which spin to flip, backtrack like the PLL, these kind of things. If you do that, this becomes NP complete right away. Okay, so it's a hard problem.
As an organizer, I should apologize that we ended up starting 15 minutes early for various reasons.
But I haven't
and
said
that-
anything. So.
And that, right, but I promise that at 1:30 we will pause, we will, you know, so we'll have a couple more additions, but you also just quickly recap and see if there are any questions. So can you recap what?
So let me recap quickly. So what we're gonna look at is XORSAT. And we're gonna look at some classical algorithms to solve XORSAT, identifying the issue of the difficulty of the solution of the problem into what are called entropic barriers. And then see how these entropic barriers affect the quantum adiabatic algorithm as well. I was just describing XORSAT, which is a set of M parity checks on 3, in this case, variables. Okay. In principle, I was saying you can solve this problem by Gaussian elimination because it's a set of linear equation in a field. But
Can you explain? I guess I think I understand that, but so those clauses look like a linear equation, is that right?
yeah,
Well, how do I see that?
Some 0 and 1 is
it's a
more
sum.
two.
It's a sum.
It's a sum. It's sum in F2.
Yeah, okay. What is F2? So
And fields modulo. Field of integers modulo.
right, yeah, and then that one is a product like,
This one, yeah, it's nonlinear. You can think of it as a.
gotcha, okay.
So,
thank
but
you.
you mentioned that this could have no solution, right?
Yeah.
And then you mentioned something about the rank. Are you looking for a subset of where the solution is available and things like that?
No, typically you ask whether
Just
the
if there's
entire.
a solution.
Yeah, either there is a solution or not. If there is a solution, the formula is said satisfiable. If there is no solution, then the formula is said unsatisfiable.
Okay, so you could simply check this by the determinant per se, right?
Yeah, exactly. Yeah, exactly.
So
You have
this
to
is-
compute the determinant,
So
if you want, in the field
And,
F2. So this
and
is
this
simple.
doesn't grow exponentially.
This doesn't grow
This is polynomial. I didn't understand the exponential part that you mentioned.
Yeah, so the exponential part is the following. If you have an algorithm which doesn't do that,
Mhm.
but just takes this as a spin model, and now we're going to write the Hamiltonian for this thing,
Okay,
and you don't know this actually is actually a linear problem in disguise, but you just take it as a Ising spin
okay,
glass, okay, and you run Monte Carlo on it,
Okay.
you're going to get stuck, okay.
okay.
Same is true for the linear problem as well.
Yeah, this is for the linear problem.
Right, yeah.
You don't get stuck for in the linear problem. Okay.
Yeah,
Yeah, it's not for Monte Carlo. Either whether you add a fraction of 3 SAT clauses or not, it's
No.
completely irrelevant.
but
The solution time is exponential in time here.
So now the scaling is the following. You send n to infinity, and you send m to infinity proportional to n. And then what you find is that now you generate the random formulas, and you ask what's the probability that the formulas is sat. Now for as a function of alpha. If alpha is 0, clearly this probability is 1, but then the interesting thing is that this thing actually is 1 up to a certain point, then it has a phase transition. And there is a critical alpha, which is something like 0.918. Okay.
Does it lead to any discontinuity in some thermodynamic or?
Yeah, it's a discontinuity actually. You can actually zoom in here and look at the. So clearly you don't see this when you do numerics.
Yeah,
What you see is this, right? So if you try to do, so as you increase the system size.
But what kind of transition would you get? Like
It's
first
kind of a
order or
second
second?
order. It's kind of a second. Okay. But this exponential difficulty arises only for alpha larger than something else. Which is 0.83. Okay, this is called dynamical threshold. So here the problem is kind of easy. Here the problem becomes difficult.
So do I understand correctly that the transition, the transition to existence and that, that's basically when the system becomes
Over constrained.
Over constrained, yeah.
Exactly. That's exactly correct. You find the same transition in random 3-sat, k-sat. Whenever you have random formulas, if you adjust the density properly with the right scale, then you can get the transition. And typically in the region around the transition, not only on this side, okay, but also because, you know, if you, so to prove that a formula is unsat, you not only have to fail to find a solution, but show that there is no solution.
Right.
Okay, so a complete algorithm. A complete algorithm is such that if there is a solution, I give you a solution. If there is no solution, I give you a certificate that proves that there is no possible solution to that problem. Okay, this algorithm will run in exponential time, also in this region here. So it's like saying Monte Carlo. Okay, I do my sweeps and I do parallel tempering, whatever fancy method I have. I don't find that the energy is zero. Don't find the configuration energy zero. How can I prove that there is no configuration of energy zero? I have to be smarter than that. I have to find a contradiction, for example, between the clauses.
But Gaussian elimination would have no issues with that. It just keeps running until it says, whoops, no, these were
Yeah,
two.
the rank is to
the rank, yeah.
forget.
Okay.
There is a solution.
Okay.
Okay, good. Now, what happens here in this region here? It's attributed, the difficulty here is attributed to the fact that if there are two solutions, if I have a solution X, which is a set of bit X1, let's say, and another set X2, which are solutions, either the two things happen. The distance, the Hamming distance between these two solutions, it's either smaller than a certain distance d1, which is of order n. Okay, that actually it means like this. The Hamming distance between the two solutions is either small or large. So if I take two solutions, if I take a solution, there's a bunch of solutions here, then there is nothing here, and then there is a bunch of solutions here. Okay. So this is called clustering. So solutions cluster in balls on the hypercube, which have a certain size, which is.
And how many of these balls are there? Are there exponential number or
There are typically an exponential.
distinct balls? There's
Yes.
enough room.
Yes.
Put all-
There is a complexity which measures the number of clusters, which is everything is exponentially large. There's an exponential number of clusters. In each cluster, there's an exponential number of solutions.
And the exponential number of clusters somehow, the coefficient, the degree, the entropy of these clusters somehow smoothly evolves between those two
Yes,
limits.
yes, yeah.
So the clusters are progressively getting smaller and smaller and smaller as they become bigger.
Yes.
Somehow.
No.
They're becoming more numerous.
Well, okay, here I have to say this is more an art than so there are people that have a lot of experience with this, and they will tell you that what happens is that at the beginning, in the easy phase, all the solutions are in the same cluster, you can move along there easily, right? Then they start to break down. Then, and let's suppose this is the only discontinuity that happens, okay? Then the number of solutions in each of these clusters starts decreasing. until there is no solution in any cluster. You still have an exponential number of clusters, but all of them are just,
One solution.
yeah, exactly, one solution, and then you, here, at this point, you don't have any
Yeah.
solution.
Okay, that makes sense.
Okay, good. Now, source set is also nice for the following thing. You can plant a solution in source set. Very easy. Just put this. Okay, and then the solution is that all the x's are zero. So it doesn't matter how many clauses you put. You can put as many clauses as you want. You are always going to have at least one solution. Now, typically, when you do this, this is an artifact, right? So now, so let me show you. So graphically, this looks like this. On the vertices, I have variables, and this is a clause, right? And then it's a random hypergraph. In which, and so on, okay? So each clause is made of 3 variables, but each variable can be part of many clauses. Typically, when you do this, you get that each variable is part of a number of clauses n, which on average is 3 alpha, because on average is 3 alpha, and in k alpha. In any case, n is Poisson distributed. Okay, good. Now, each of these clauses has 0 here as parity check. This is like a ferromagnet. And the Hamiltonian is just sum of the clauses. Sigma A general one A.
So when you create these clauses, do you restrict the indices to be close together? Because if I, or no.
There is no, so when you create the graph, when you create the formula, you do like this. You take n bits and then you throw at random.
Okay.
Now, when you do this, you're creating a random hypergraph. A random hypergraph locally has no loops. You can think of this as also when you build a random graph. Also, when you build a random graph, you have no loops. Why? Because I have, okay, I've chosen these two to be linked. Okay, then I've chosen these two to be linked. And then I have to choose what to link this with. But I have n minus 2 other spins to link with. And to make a loop, I only have one of them. So the probability that there is a loop of order 1 is 1 over n.
Okay.
So locally, if you look locally at a random graph or hypergraph, then you see no loops. Okay, the first loop you see at the distance, which is with probability 1, you have to go to distance, which is logarithm of the number of vertices.
But
So the localities arising automatically.
so in physical terms, if I were to consider this Hamiltonian, this in principle can interact, like any spin can interact with any other spin.
Yes.
It just, the only
In the
constraint is that.
ensemble of Hamiltonians, yes.
they
But
have-
once you choose the realization is a locality. You start from the one spin and you move around, and you're not going to make a loop and come back
Right.
with probability 1.
But why can't I just put a large triangle, like take that leafy thing that you drew? I mean, I can just put a very large triangle and mess your locality. It's locality.
These of course with probability 1 over n. That's what I'm saying.
Right, okay.
You can do that. This
Yeah.
happens when you generate these random formulas.
Yeah.
This happens, but this happens with probability 1 over n. in order to find, so, yeah. Okay, so you can okay, so this is a ferromagnet. And I always have a ground state of energy 0, in which I select all the spins to be equal to +1. So this look like, and yeah, what I wanted to tell you is the following. Now, even if I do this and I run an algorithm starting from a random configuration to find the ground state, I'm going to get stuck. Exactly, irrespective of what the B's are, I'm going to get stuck. Even Monte Carlo gets stuck here. Why? Because it's sufficient. One of the spins is actually -1, and then this becomes an antiferromagnetic. So you have self-generated frustration, an antiferromagnetic plaquette, and you have a self-generated frustration. Good. This is not the case, for example, in TRISAT. You can plant solutions in TRISAT. It's not as easy as doing this. Typically, what one does is the following. You choose a bit configuration that you want to be a solution, and then you throw random clauses. And if they are not satisfied by that, you just don't. It's like a rejection algorithm, right? You generate random clauses. If they are not satisfied by that configuration, then you don't add it. Okay. When you do this, the ensemble that you get, the planted ensemble, turns out to be easy. You run an algorithm on it, and it just flows to the solution. For XORSAT, this is not the case. Even if you plant it, this was recognized in a paper from the early 2000s by CBO France and other people. Federico was part of this paper.
What was written, the easiness of the planted solutions? Or
No. So they didn't look at XORSAT, they looked at this ferromagnet here, and then they say that this one is a spin glass with replica symmetry breaking, even though it's a ferromagnet.
Okay, actually, I don't like calling it ferromagnet because it's not spontaneously ferromagnetic. The 3-spin interaction basically is like a field. It's more like
the ground state is all spins pointing in the same direction. What would you call that?
But there is no, sorry, if the all spins point up versus all spin point down, that's not a degenerate manifold.
No.
Right, that's not a ferromagnet. Ferromagnet is spontaneous symmetry breaking usually. Paramagnet is when you put a field, I can put a field and line everybody up. So fine, as long as it's an interacting paramagnet.
What geometry do they define this?
Say it again.
On what geometry do they define this?
Random geometry. Exactly the same thing.
But random in the sense that it's all to all.
No, it's not all to all.
No.
It's potentially all to all, but it's random triplet choice. It's on a random hypergraph.
Okay.
Okay.
Yeah, let me probably refine this. Can we actually see in which dimension this hypergraph fits in?
Infinite. Because how do you define the dimension of an object on a lattice? You look how many points there are at a given distance, right? In random graphs, random hypergraphs, and random graphs in general, you take a point, you count how many points there are in a given distance, and it's exponential.
Okay. So in the limit, it's going to go to
I think one way that people frame it is that if you draw this ball, you want to know how many points are on the surface versus bulk, and it scales the same way.
Yeah,
Basically, surface to volume ratio is 1.
Okay. Yeah.
Always.
Right.
Pretty pathological.
So stated the antiferromagnet is also a metastable solution.
So there are a lot of metastable solutions of this thing, and what they found is the following. So if you I have to decide what to sacrifice. I can sacrifice this. As a function of temperature. Now you can solve this problem. It's a mean field problem. You can solve by writing mean field equations to it. You have to be a little bit more. This is like beta equations for beta mean field equations. And these equations have three possible solutions. Okay, one ferromagnetic, one paramagnetic, in which the expectation value of the spins is 0. Okay, one ferromagnetic in which the expectation value of the spins is larger than 0, all of them. Okay, and then there is a spin glass solution. And if you start, so there is the paramagnetic branch, and then the ferromagnetic branch, which has first order transition here. And then, if you come from large temperature and go down, like in simulated annealing, for example, you don't get to the ferromagnetic solution. What you do is your paramagnet gets stuck into spin glass solution.
There's a mean field calculation that gives this result?
Yeah, the mean field.
I didn't know. Okay. So you actually get multiple states?
Yes, yes. And you get a minimum for this energy here of spin glass, which is something which I haven't written down. But you can look at this Silvio Franz et al. Federico Citasenghi, Marc Mézard, and some other people. And this is Europhysics letter 55 465 2001. Yeah, no, I've written down. It's actually very tiny, this thing, because this is 0 and this is 0.0183.
Question.
Okay. So the idea is now that when you take this problem and start applying Walsat or any other algorithm, now let me define Walsat, what it is. If any local algorithm that does these things, then you're essentially following this curve here. You start typically from high temperature configuration, and you want to get the energy down by flipping spins. So when you do this, you don't go to the ferromagnet, which is completely disconnected part of the phase space, but you end up in these things here. And then eventually you're going to find a solution. But what happens is that energy number fraction of unsat closes. Okay, you start from something, and then you quickly go down to some energy, which depends on your algorithm. Okay, and it's not necessarily this thing here, but it's larger than that. You stay here a very long time, and then you hit by complete chance the right sequence of spin flips that brings your energy down as a function of time, and actually log time. And this thing here is order n. Okay, so it's an exponentially large time. This thing here is time over the 1.
How different is that from any other first order phase, if you had a first order phase transition? If I just do Monte Carlo, how do people generally equilibrate across first order phase transitions? You do need to like a large Hamming distance move to.
Yeah, it's similar to that, but the issue is that here you don't typically it's like decay of false vacuum, right? That's what you have in mind. Right?
Yeah,
You have decay of false vacuum. You have to go from one.
You have to
There was this situation, and then it evolves, and you were here, then it evolves like this, but you're still here, and you need to jump over here.
Mhm.
You need to create a bubble, let's say, and then this bubble takes over.
right, exactly.
So I think this is morally the same thing. What the one big difference in my mind is that this is infinite dimension. Infinite dimension, then the cost of the energy. So you create a bubble, and the cost of of true vacuum in false vacuum,
Mhm.
and then you have to pay an energy due to the boundary conditions of this thing.
Right.
Okay, and so that's large, but not too large. But once you have done that, then you start realizing that you can actually optimize, and then your bubble grows.
Mm.
In fact, if you look at Coleman decay of false vacuum, what happens? You create this bubble, and then this thing just moves at the speed of light, close to the speed of light. Okay, but here the space has infinite dimensionality.
Yeah. Okay.
So
Good.
you pay as much energy on the boundary for the bubble that what you're getting.
Okay.
So that doesn't happen.
Good. Okay.
So I think the dimensionality issues.
Well, I think the other thing that happens, of course, in that false vacuum thing, in the physical model, there will be a temperature below which the vacuum is no longer locally stable. And then you can just, you become, but here presumably you remain locally stable to much
Yes.
lower temperatures.
Yeah.
That's another sort of a weird
Yes.
thing.
And I think that's due to the infinite dimensionality.
Also-
I think most of this phenomenology found applications in algorithms and the formula. So because underlying there is infinite dimension.
Mhm.
When you try and look at this phenomenology at finite dimensions, everything comes in your way. So it's still debated whether the infinite dimensional the picture of infinite dimensional spin glasses applies to 3 dimensions. So clearly it applies to these things. Okay. Good. So how can we see this? Now, in the interest of time, okay, let me tell you first what one can do in general. So there is an algorithm WalkSat which is easy to analyze and shows this thing here. But one thing that one thing that I want to make clear is the following: whatever algorithm you do, you come up with, which is a variation of like pick a clause according to a certain condition, flip the clause according to a certain condition. Okay, it's going to have this behavior, and this plateau here, it depends on the algorithm, and it's above this energy of the zero temperature energy of the glass phase, which is typically around here.
So before, sorry, I should have asked this before.
Yeah.
So for a general like choice of clauses, the probability of having degeneracy is almost 0, right?
Yeah.
It's like
Degeneracy
1 over n to the cube, something like that, right?
Yeah. You mean by degeneracy, you mean the same energies?
Yeah, the same ground state. They have 2 ground states.
Okay, since we have planted a solution here, we always have one solution, right?
One
at
for
least
sure.
at least one solution. Then the way to get only one solution is to crank up your alpha. You crank up alpha, you know that it's going to be one solution, and you are guaranteed that it's not going to be
Then
anything
it's gonna
else.
be like 1 over n cubed, right? The chance of having. No,
Yeah,
even less,
something like
right,
that.
right.
So
Okay. So there's no, by chance, it's almost like almost surely that it will never go to the second ground state
Yeah,
because it will most likely not exist.
yeah.
Okay.
You need to have many ground states to have a chance to get there,
Okay.
exponentially many. If there are two, it's like
Yeah.
there is one.
Yeah, but it seems like false vacuum analogy is inaccurate here because of what you just said, because you're not in the correct thermodynamic minute, whatever, the correct state for the spin glass state, right? You're not tunneling from the correct thermodynamic thing, because you're still wandering down the entropy.
You mean here?
Well, the fact
For
that you,
example.
yeah, so if I wanted to think of a first order transition from a spin glass to a ferromagnet, I
Uh-huh.
would think that you would be in a Gibbs state in a spin glass, and then you want to make a
Yeah,
transition.
so you are not in a Gibbs state
You're
here
not in
because
Gibbs state
the
yet.
dynamics that you have
Stuck, yeah.
chosen, no, the dynamics does not respect, for example, detailed balance.
Uh-huh. I
So-
see, okay,
So this analysis is for anything that respects detailed balance.
right, I see.
Okay, so if you did simulated annealing, slowly lowering the temperature, then that would be
Mhm.
what you would find, okay? But typically, algorithms don't care about detailed balance. Actually, on purpose, we try to break detailed balance. And therefore you get stuck somewhere,
Mhm.
okay? And for a very long time, and then you go down. And this energy, there is nothing glassy. You're like up here. Okay, so there are no barriers to overcome, nothing. So why do you get stuck here? That's the issue.
Right, okay.
Okay, and these are entropic barriers. So there are way too many directions at that energy. There is way too much entropy at that energy to allow you to pick the golf hole, right? The hole for the golf ball to go. So, for example, what we did is analyze an algorithm. So we came up with some quasi-greedy algorithm in which so you can divide your bits by the number of clauses that they violate. Okay, so every bit is known to be part of, I don't know, 5 clauses, and 3 of them it violates. Okay, and so this is a K. Now for this, I'm not gonna go to the Poissonian random graph, but I'm gonna go to the regular random graph in which each bit, just for sake, you can do the same thing with Poissonian. It doesn't really matter that much. In fact, for work set, it's better to do the Poissonian. Each clause is part of 3. Each variable is part of 3 clauses. Not only each clause contains 3 variables, but also each variable is part of 3 clauses. Okay, so K can just be 0, 1, 2, and 3. And you call Fk the fraction of such variables. Okay, so it's the number of K variables divided by the total number of variables. Clearly, this sums to 1. And then to define my algorithm, let me define some arbitrary weights Wk, which are the weights by which I
Sorry,
pick.
can you just very quickly repeat, what is this definition you made?
So a K variable is a bit that is part of K unsat clauses.
Mhm.
So a bit in K of a zero variable is a bit which is part of no unsat clauses. All the clauses that involve that bit are already satisfied.
Mhm. Mhm.
Okay?
So all this is in the context of a fixed configuration, I guess.
Yes,
Okay.
absolutely.
Yeah.
You generate your random graph and then you generate your initial random condition. And now I have to give you a set of rules to update these conditions such that hopefully we're going to get to the ground state. That, by the way, we know what it is. So it's okay. So you are allowed to play with these weights WK. Let's say that I pick a clause of the type K, a variable of type K with probability proportional to WK. So WK, FK, and then I normalize it by. Okay. Now, believe me if I tell you that worksat, which I haven't defined yet, but in case I will define, just to keep in mind, worksat that for that worksat WK is K. So you never pick an unsat clause, you pick with probability with weight one, a bit which is in one unsat clause, two, which is two, and three, and so on and so on. Good. Okay. Now you have this clause here, okay, and then you have to pick a variable, okay, and then it depends how many clauses there are. There are 3 of them. Now, there's gonna be an F0, F1, F2, F3. So if you, for example, if you pick a variable of type 3 and you flip, then delta F3 is gonna change by -1 over n. Okay. And delta F0 is gonna change by 1 over n. Now, things become a little bit more complicated if you want to look at what happens at the other things. But for example, delta F2 is going to be the number of variables that go from type 3 to type 2 minus the number of variables that go from type 2 to type 1, and this is divided by n. Now, these are random variables. And you have an equation. So you have a random, where is it? Random set of equations, sorry, a set of equations for F, which make a random walk, okay? And you can do, now you have to do some assumptions, right? If you want to do something with these equations. So, okay, you can either run the algorithm or try to do some analytics. Suppose you do the assumptions in which the variables, these numbers are all, the numbers here, the random numbers here are all uncorrelated random variables, okay? So every time I do this, I don't care about if there is any correlation fixed between this spin and the surrounding spins. This is in some sense true if the energy where you are is sufficiently high. If you do this, you can write a set of equations for F. And
Have you explained how worksat works, or is that what you're explaining?
I'm going to explain how it works.
Okay.
This is a generic algorithm. This is what I wanted to show you the generic algorithm first. for arbitrary choices of W, because we then, in the paper, we optimized over W to find what happens. And you find that, so you can now write this random stochastic processes for F. And then you can now take averages, assuming that everything is uncorrelated. And you get a set of nonlinear differential equations for F, which look nasty because F is also in the denominators here. So I can give you an example. For example, the equation for, just to show you what it feels like. No, it's not that. The equation for F0 on average is W3F3 1 plus 6F1 over Z plus W2F2 4F1 over Z minus 6F0 over Z.
But it's a four-dimensional system of equations.
It's a four-dimensional system of nonlinear differential equations.
Okay.
Plus other two terms divided by W3F3 plus W2F2 plus W1F1 plus W0F0. And Z is 3F3 plus 2F2 plus 1. It's this thing here. Okay. And then there are three other equations which look as nasty as this. So you might think that actually that has nothing to do with what's going on. But in fact, let me share the screen.
Let's see if that. Okay, good.
Oh, can you see it?
Yeah, I can see.
Okay, maybe you can see over there. I can show you
Sure.
guys here.
Yeah.
Okay, so
So this is just to model the behavior of your
of the algorithm. Yeah. So you see, these are choices of W's, okay? And the dots are the results of running the algorithm, and the straight lines are the results of solving the differential equations. They're on top of each other. Great job, okay? So there is no correlation. It would be nice then, I can tune the W's in such a way that this actually flows to zero. That would be too nice. In fact,
what flows to, sorry, I didn't.
the fraction of unsat clauses flows directly to zero because now I have control on this.
Okay, but where is the exponent? Where is the quasi plateau in these solutions? I don't,
Here.
maybe I missed that.
I think
Here.
we got it, yeah.
Okay. So here, for example, WOXAT,
The red one.
it's the red line.
Mhm.
And it plateaus to some value, okay? Then there is another choice, which is the green one, which plateaus in another thing. And then for the analytic, the plateau of the
Wait,
blue...
so it's figure 6 that we should be looking.
Yeah, figure 6. For the analytics, it will tell you that the value of the plateau is less than the energy of the spin glass.
That seems wrong.
And that seems wrong,
Because the assumption breaks down.
because the assumption breaks
Yeah.
down. Okay. But so it breaks down somewhere up here. Okay. So the algorithm and the nonlinear differential equations, they depart.
So what's different between red, green, and
The choice of W. So you see W in the red is 0, 1, 2, 3.
Mhm.
In the green is 0, 0.111. I mean, these W's are completely, as I said, you don't have to respect detailed balance.
So W's are the parameters in the algorithm.
Yeah.
Okay. And it seems to me like the most aggressive ones are the best or whatever on this scale, but that's where you lose the.
So,
those kind of-
now there is an issue. This doesn't guarantee you that solution time is smaller. The fact that you go further down, closer to the origin, doesn't guarantee you that the solution time is small.
Mhm.
because the solution time is not described by the plateau.
Can I ask a sort of a kind of a practical question?
Yes.
I mean, I don't have a lot of training with dealing with nonlinear systems of equations. And my general sort of a question, like in the last couple of years when I come to this, I said, okay, first thing I want to do is if you tell me that there's a steady state, I don't want to deal with time dependence. I want to look
Directly at the
state.
steady state, yeah.
So is there but what you're finding here is that in the most potentially interesting regime, the steady state is out of reach of these equations.
Yes.
So that's not,
Yeah.
that's bad.
That's bad. However, just to say, if we, so there are two things here. There is the random process, okay, and there is the average random process. Okay, so the average random process, it goes to a plateau and whatever, but the random process might actually give you a solution. And this is what I want to show you in the simplest case of worksat, because the other cases we actually didn't work out. And in worksat is very simple. So what's worksat? So worksat, first of all, in this language corresponds to WK is equal to K, but I don't want to use this language because this is a much simpler expression. I can write directly the equation for the number of unsat clauses. Okay, so what is worksat? Worksat is the following thing. You pick a clause and you flip a bit. You pick an unsat clause.
Wait, can I just ask a
Yeah.
quick question? So the algorithm that you devised still has randomness?
Yeah.
So you can derive like Fokker-Planck type.
That's
I mean,
exactly.
this is basically what this is.
This is the average Fokker-Planck.
Uh-huh.
Okay, so
Okay.
the average Fokker-Planck tells you the plateau and tells you the initial. So it explains this initial part, and explains the plateau condition to the fact that the plateau is not below the glassy value here. Okay. So if the plateau is below, then the Fokker-Planck average description fails.
But the transition to the true ground state is out of reach of this Y. The true firm.
The average, but not the Fokker-Planck. That's what I want to show you now.
I see. Okay, right. So if you had the full distribution, you might actually pick
Exactly.
up that the tail is doing
Exactly.
something. Okay, I see. Mhm.
So and worksat, what you do is, I say that you pick an unsat clause, just flip a bit.
Mhm.
This makes that clause sat, but makes other unclause unsat. Okay, so delta, the energy change is -1, and then you get the number of excess clauses which were sat become unsat. So you get a positive contribution to the energy, and the number of excess clauses that were unsat, they also become sat. Okay, good. Now you want to average this on an interval of time, delta t, which is much larger than 1, but much smaller than n. Okay, because you want to do a coarse-grained view of this thing. And so the number of
Sorry, is it temperature or time there?
time, now it's
Okay.
time, sorry. Okay, now, so you have to add all these things here. So the change in delta H is gonna be minus delta T, okay? And plus the sum over S over delta T steps minus the sum over U over delta T steps, okay? Now, on average, the number of excess unsat clauses is this is for, we call it here P peaks of sat, okay? So you have P clauses, okay? So the number, this thing here is also a random number, okay? Which on average has P, the fraction of clauses which is unsat, times delta P. Okay? This is the average value. And then there is a random number. There is a random number here with the random Gaussian distributed number between 0 and 1, and then the amplitude of it.
Hi, is it, I think those of us who are on Zoom are not
S
seeing
is-
what's going on here.
E alpha minus alpha u times delta t plus a random number. So R1 is Gaussian with average 0 and if now I take these two and I put here, then delta H becomes minus delta T plus P alpha minus 2 alpha U times delta T plus R, now also R is square root of P alpha times delta T. Okay. And now I can write an Ito equation going to delta T, which is delta T over N. Okay. And I can write it for the fraction of clauses which is unsat.
Hey, Antonio, can you close your screen? Because apparently,
sorry.
no, the share, yeah, okay, there we go.
So delta alpha u, it's then I'm gonna rewrite this thing as 2p p alpha minus 1 divided by 2p minus alpha u times delta t plus square root of p alpha over n pw. Okay. So now this is the Ito equation from which we can get the Fokker-Planck equation. The Fokker-Planck equation tells us the evolution of the entire probability distribution. And let's see what happens. So, first of all, notice that there is alpha u here, and this is some constant. Let me call it alpha 0. Okay. So it's like an Ito equation for a harmonic oscillator, because this is a restoring force. Okay, so there is a restoring force like this, okay. And I can write down the Fokker-Planck equation, dp by dt, equal minus d alpha u, 2p alpha 0 minus alpha u times p plus 1r okay. So this has an equilibrium solution which is centered around alpha 0. And there is a diffusion coefficient which is of order 1 over n. So this probability distribution at equilibrium, so there is, so whatever you start from, you start somewhere over here, I don't know. Then your probability distribution for the fraction of unsat clauses is going to evolve quickly because of the restoring force towards something which is centered around alpha 0. And then eventually in this time scale, at infinite time, it's just gonna go to a probability distribution which is proportional to e to the minus 2n divided by alpha u minus alpha 0 squared. But this probability distribution is non-zero at the origin. Okay, so you're going to spend most of your time around alpha 0, but lucky coin flips in your random process will bring you up here, and therefore you can get the time to find the solution as the inverse of the probabilities which are computed at alpha u equal to 0, and this gives you e to the 2n, actually n times some quantity here, okay, in which you put this equal to 0, okay. And if you compare that with the numerics, you get this figure 7 here. So the dots are numerics, the red curve is that formula over there, and this blue curve is some large deviation calculation that was done years ago by Semerjan and White, I think. Hartman. Either Hartman or White and Semerjan. So this actually fits well the data. And the argument is again the same. This Fokker-Planck equation tells you, okay, you're going to live on this plateau, which corresponds to the minimum of the average forces forever. And then at a certain point, you're just going to go down. So, and this is an issue of entropy. It's not an issue of barriers. This isn't barriers. It's just. Okay.
I'm curious. So I have a general question, maybe confusion about entropy. So entropy is not a local. So can I look? Is there a notion of locality? Is this a problem with infinite dimensions again, where you would think that if I just had any kind of locality, I could locally look and say, I would like to drain some entropy here, please.
Yeah.
And entropy is not local, but it's approximately local, and so you can actually reduce entropy of any one local area.
Yes.
Somehow physically.
Yeah, when you are in infinite dimension,
Okay.
that's an issue. But in fact, it looks like the difficult problems might be in infinite dimensions. Typically, I mean, I'm sure you can. The worst case, some difficult problem can be probably put on.
But there's no finite dimensional versions of this problem, because I thought that there was at least some controversy in the proper spin glass field whether infinite dimensional solutions tell you anything about finite dimensions.
Yeah, sure.
There was an idea that somehow some of these features survive to three-dimensional spin glass.
That has not been solved yet, but I mean, that's the physics of spin glasses. Okay, this is a different animal. Okay? This is more computational complexity. I mean, performance of algorithms than other. And typically, those naturally live in infinite dimensions where there is no controversy. I mean, this.
Right. No, I'm just curious how much of this is just. So the
Can be ported to finite dimensions.
Well, no, yeah, I guess there's no notion of locality where I can just kind of like reduce entropy.
Yeah, and then I quickly wanted to tell you about what happens when you do quantum annealing.
Wait, I thought that was on Thursday.
No, on Thursday I wanted to discuss something completely
Okay,
different.
all right.
Some experiments we have done with
Okay.
NV centers and
Okay.
optimization of
Okay.
quantum control.
Okay.
But I mean, there isn't much that I can tell you, except that, you know, if you look at the time to reach a solution defined. So I didn't want, so we didn't, because of these many states here, we didn't want to define the time as 1 over the gap. Okay, we really wanted to do the following thing. Take your Hamiltonian, which is you know, T over T times the classical Hamiltonian plus E minus T over T of the quantum Hamiltonian, which is just transverse field. Okay, and this one H0 is that over there. And then solve the Schrödinger equation.
But the idea is that you don't raise the energy, so you're always sort of at the same, you're below the energy of the spin glass.
No, the idea is that you start with the at t = 0 with this Hamiltonian here,
Mhm.
which typically has an energy which is very, so in this thing here will be like over here.
Oh, I see. Why?
Okay,
Because
because
that's
this
up
is
to you,
infinite
isn't it?
temperature. This one is
Oh,
just
you're not
sigma
putting it
x.
in the ground state.
The
Sorry,
ground state of H1 is
Yeah.
infinite temperature in this thing here, because it's a random state for this Hamiltonian, so it's infinite temperature.
But the true energy is minus M.
The true energy is minus
So it's actually below that energy. I mean, from the point of view of I think the quantum adiabatic algorithm was that the energy is a quasi-conserved during the sweep.
Yeah, but the Hamiltonian changes. So the fact that the energy is quasi-conserved means that you start from this energy, you go to this energy here. This ground state here. But if I take this state, ground state of H1,
Mhm.
and I look which energy
Right, no,
that corresponds in H0, the energy is like infinite temperature.
but that's, never mind, since we're at the end, I wanna hear what you have to say. I'll ask my questions later.
Okay, and then how you define the time? You say, okay, now I'm gonna evolve this for time t, which is fixed, and I'm gonna look at the probability that in time t, the weight on the ground state of H0, this is this, right? Psi 0, okay, times psi evolved for time t squared, and this is P of t, and then I want that this P of t is larger than epsilon, and this epsilon does not scale with n. And then this gives me T of n epsilon. So I don't talk about gaps or anything, but I have to solve, you know, I have to do a Krylov evolution, time evolution in Krylov subspace of this thing here. This gives me T of n of epsilon, and T of n epsilon is some prefactor which depends on epsilon. And then there is a factor, exponential factor, which does not depend on epsilon. And you look at this mu, and you have an exponential growth, which in fact you observe in these things. Okay, and this, we think in this problem has much to do with the fact that you have a lot of states close to where you have the crossing. Now, I don't have time, so this sounds like nonsense. Maybe it is. We're convinced that it was not. So the issue is not of barriers, of tunneling through barriers, but the fact was that the probability, there was a leaking of probability towards the high energy states, okay? And even though this leaking was exponentially small, there were exponentially many of them. And so you're left with an exponentially small probability of staying in the ground state. So the physics is slightly different from that of tunneling through a barrier. And I will stop here.
Okay, let's thank Antonello. Let me check, are there any questions? Wait, just a minute, please. Yeah, are there any questions online? Otherwise, we're gonna ask questions here and wrap up. And there's a follow-up, well, there's a different talk on Thursday. If you wanna come by, please, go to RSVP so we order lunch. Okay, any questions online? No? Questions here?
Oh, we had many questions.
Okay, all right.
I don't
Well,
feel neglected.
You don't feel neglected,
I
okay.
don't.
All right, thanks very much. See you maybe on Thursday. See you on.